Welcome, everybody. We'd like to bring up our next presenter, Kent Anderson. He's the Principal Program Manager, Machine Teaching Innovation for Autonomous Systems at Microsoft. Kent is going to share his thoughts with us on teaching AI skills and strategies with the title, Don't Try DRL Without This. So welcome, Kent.
Thanks, John. It's great to be here. Thanks for inviting me. Glad to be at the AnyLogic conference. And just like John said, my name is Kent Anderson. I work for Microsoft in autonomous systems. My focus is teaching machines advanced AI. And this is exciting, a part of the simulation world these days, where deep reinforcement learning, which is a new form of AI, you've probably heard of it. It's the AI that beat a bunch of Atari games. It beat grandmasters at the game of chess. It beat the best Go player in the world in 2016. And we've been spending the last 3 or 4 years figuring out how to use that kind of decision-making, strategy learning, perceptive AI in industry. And actually, you'll hear about it in other sessions, making decisions in logistics tasks and, in warehouses and all sorts of things. And it's very exciting because the AI learns by practicing in a simulation. And so AnyLogic is one of the most well-integrated simulations to our low-code autonomous AI platform. It's called Project Bonsai. But I wanted to talk a little bit about first why this kind of AI is promising. But then I want to spend most of the time talking about how to make this kind of AI work in real life. And so first, the why. Automated systems have limits. So whether it's you're using a control system or whether based on control theory and your system is calculating what to do next, or probably for most AnyLogic customers, it would be an optimization routine that's searching a space for options. Maybe you're using Monte Carlo simulation. There's 3 things that I hear over and over and over again about why folks are considering AI and hopeful that AI can provide additional capabilities. One is that they're static and rigid. So, whether it's a control system or, an optimization routine or even an expert system, once that behavior is set, is programmed, it's not going to change. But AI, this kind of autonomous AI can absolutely change its behavior and behave differently. Even after it's trained, it can behave differently based on the feedback that it's getting. Probably the most common thing I hear is that, these systems can't consider all the relevant data that us humans would consider. Imagine things like looking at an image and that helps you make a decision. Imagine how we make logistics decisions by looking at maps. And there's all sorts of rich visual information on that map that, an optimization routine is not going to be able to pull out of an image, for example. Auditory signals, categorical information. There's just so many things that this autonomous AI can actually look at and process and use to make decisions. And then the third is, I call it lacking imagination, but it does look a little bit like creativity and imagination when you're working on a specific task. But it's basically a delayed gratification. It's the ability to say, I'm not going to do what the objective function or the calculations might say is the absolute best thing to do right now because I know something about the system. And so I'm going to wait and I'm going to get better results later. And so to us and to me, what an autonomous system really is about is AI-powered automation that makes decisions by sensing and responding in real time. I have a short 60-second, our talk is 60 minutes, a short 60-second video about our approach.
In business, disruption can come at any time from anywhere. The key is being agile enough to respond. By building autonomous systems, your organization can better adapt to change and consistently deliver customer satisfaction. No one knows your operation better than the people who run it. Microsoft Project Bonsai gives your engineers a low-code platform to create AI-powered automation for your existing processes and equipment. No data scientists needed. Add intelligence at your own pace. Start with a single control or process, or transform an entire system. Guided by your engineers, the AI learns in a simulated environment, testing millions of scenarios safely and without creating downtime. Once deployed, the AI monitors all process variables and makes or recommends adjustments in real time to help you generate more consistent quality and reduce waste, increase efficiency, and prepare your business to respond to change so you can deliver without interruption.
Okay, so we know that there's a new form of AI called deep reinforcement learning that can do some pretty amazing things, that can make more human-like decisions. It can make decisions by looking at images. It can make decisions in response to sounds and categorical information. It has this idea of delayed gratification. It can change its behavior and adapt to feedback. Okay, this is all very powerful. Okay, Bonsai, Microsoft has a low-code AI development platform called Bonsai, but I'm not here to talk to you about either of those things specifically today. I'm here to talk about what I learned while designing over 100 of these autonomous AI over the past 3 or so years. And what was most interesting to me that I learned is there is a huge amount of amazing subject matter expertise, experience in all these things, whether you're talking about warehouse optimization. So I'd go to a warehouse and I'd talk to the experts that run the warehouse and that schedule and place the items in and pull the items out. Whether it's talking about safety stock or inventory optimization, whether it's talking about routing, or whether it's talking about baggage handling, these kinds of things that AnyLogic simulates very, very well, and that AnyLogic can be used as the training ground for this AI. Experts would fill whiteboards with the things that they already know about how to do this, the skills and the strategies that they already use and know and teach to each other. But then we would train these deep reinforcement learning agents and not tell them really any of it. They would explore from the ground up, from the very beginning, as if we didn't know anything. And a lot of times it would be very, very frustrating seeing the AI do things that we know for a fact are never going to result in good results. And that's really where we started to flesh out what has always been a vision for Bonsai. And is our Microsoft Autonomous Systems approach, and we call it machine teaching. The point of machine teaching is to capture and codify existing human expertise and use it as a guide for AI to explore. So we're not talking about programming expert systems and codifying rules. We're talking about doing what we do with our children when we teach them. There's a baseball example here, and of course I would never take my 8-year-old son and teach him how to play baseball by, subjecting him to 100 or 1,000 or 1,000,000 fastballs. I would guide him through a lesson plan, and I'd teach him a set of skills. I mean, the same thing when I taught my son basketball. I mean, imagine how cruel it would be, and really how foolish it would be if I took him out to the basketball hoop in our driveway and said, all right, son, I'm going to give you a dime every time the ball goes through the hoop. And maybe even a penalty when it doesn't. But I didn't tell him that the jump shot existed, or that the hook shot existed, or that the layup existed. Those are 3 time-tested ways for humans with hands and arms and legs to get that ball through the hoop. And so we're not talking about telling the AI exactly what to do and micromanaging it. We're talking about teaching it the skills and using the skills, in the analogy, the jump shot or the layup, as a framework for exploration, so that it's not trying, any old thing. And the way that we do that is through modular AI brains. And that's what I want to give you some examples. I want to give you start out with a really intuitive example that we can all understand that has nothing to do with, with most industry problems. And then I want to talk to you about, our framework for teaching skills and strategies specifically for designing modular AI brains. And I want to give you some examples from industry as well. So let's talk about walking. This is something that we all have some experience with and know about, and most of us do on a regular basis. There's actually a really fun little benchmark practice gym. It's not AnyLogic. It's from a company called OpenAI Gym, where there's this funny looking little purple robot, and deep reinforcement learning can practice, and control it so that it can try to learn how to walk. But it doesn't really learn how to walk. It learns how to do these three things. It gets down on its one knee, and uses the other knee to claw itself forward. It kind of jumps and hops, or it does what's called knee balancing, or either knee balancing down on his knees or kind of tippy-toe walking. None of this stuff meets the definition of walking, which I'll talk about in a second. But why does this happen? Well, first of all, describing how to successfully accomplish a very complex task with a single number, which is what a reward is. So, deep reinforcement learning is about rewarding and penalizing in the agent or the AI learning by practicing and getting rewards for doing things right. But how do you exactly capture and codify a complex skill like walking, or a complex skill like routing, or a complex skill like and I hear a lot of people saying, for the real problems they're working on, I've got this reward function that has 10 different terms in it, 20 different terms in it. It's because you're trying to take something complex that has many sub skills and strategies to it, and a lot of fuzzy trade-offs in it, and you're trying to create one equation that gives you a score for how well you're doing on it. And in this case, the reward function is about forward progress. So you get a reward for forward progress, and you get a penalty if you fall over. So if that big, funny-looking purple hull touches the ground, you get minus 100 points. And turns out that AI shares a similar characteristic with humans. If you penalize it a lot, it'll become conservative. It'll stop trying. It'll stop trying to do the hard thing, which is to balance, and it will get down on the ground and do things that don't require it to balance, because it's tired of getting minus 100. And that forward movement penalty is not enough to teach all the skills that are required for walking. So what is walking exactly? This is an AI that I trained using the approaches that we're talking about here in this talk. And you see, it's doing something that looks a lot more like walking. Walking is a cyclical alternating leg motion where the body vaults over the planted leg, kind of like there's a stiff leg and your body vaults over it, kind of like a pole vault. One leg is always in contact with the ground. The characteristic and why humans walk is because it's the most energy efficient way to move around on two legs. It's not the fastest, it's not the easiest, it's the most energy efficient way to walk around on two legs. And it kind of makes sense that this AI the previous AI didn't learn how to do it from the ground up, because walking evolved over literally 2 million years. And so if you use kind of naive exploration, as in, I don't teach my son anything about the game of basketball, just give him a reward for how well he does, that's naive exploration. He's going to try thousands and millions of things, and likely he's going to quit before he finds anything that's even closely resembling the things that we already know are very effective. That's basically learning at an evolutionary timescale. What we want to do instead is we want to teach specific skills. So let's look at what that means for walking. Again, this is an example that we can all relate to. And I learned how to do this by just walking my fingers on a table. I said, well, first you lift your leg. That's the first skill for walking. The second is you plant that lifted leg. You have to plant it, of course, with enough force to support the weight of your body, or else you'll fall over. And then you swing the other leg. Okay, so let's talk about teaching those skills explicitly. Here's a modular brain design where I have 3 explicit skills that I want to teach. I want to teach lifting. I don't want the AI dropping to its knees and doing all that funny looking stuff. I want the AI to lift its leg. I want the AI to plant its leg. I want the AI to swing its leg. And then I have, so each brain module here is a functional skill used for walking. And then there's a supervisor module that decides when to lift the leg, when to plant the leg, and when to swing the leg. Now, I'm not giving, and remember, these are skills. So each of these boxes are AI modules that learn how to do it. And you could see this easily by the different gaits that we have. When you walk and your friend walks, you're all lifting your legs, you're all planting your legs, and you're all swinging your legs, but they all look very differently because you're doing it differently. So that's what each of these modules is learning how to do. But each of these skills has particular characteristics. So when you're lifting your leg, you're flexing your swinging hip and curling your swinging knee like this, and et cetera, and et cetera. There's different characteristics that we already know about for what you have to do with your knee and your hip in order to lift your leg, plant your leg, and swing your leg. So why ask an AI agent to randomly explore and expect it to learn all these things? Which leads us to why we teach and practice skills separately in the first place. One of my favorite movies, and I've tried to include some media in here because it would be nice if we could all be together, but being virtual, I tried to include a little bit of media in here to make sure we're all engaged. One of my favorite movies of all times, 1984, American movie, Karate Kid. And in this movie, the karate student, Ralph Macchio, he's getting beat up at school and he wants to learn karate, and he starts learning karate from his instructor, karate master on the right. So he shows up for karate training, and the first day, the instructor he shows him a particular motion, particular hand motion, and he makes him use it to wax all the cars on the property. And there's not one, there's like 5 or 6 or something. Now, that motion that he's showing him is actually the soto uke, or the motion required to accomplish the inward middle forearm block. So he's actually practicing the same motion that's required for the inward middle forearm block, but he doesn't know that. The second day he goes and he has to paint a fence with a very particular up and down motion, which happens to be the same motion that you use for the rising block, which is called age uke. And the third day, he's sanding a floor with a particular motion that happens to be representative of the kagite uke, or the circular block. There's actually a fourth motion, which is painting the house, a back and forth motion. And so what he's doing is he's decomposing this karate blocking system into 4 separate skills, teaching each of those 4 separate skills separately, and let's see what happens.
Wax on, wax off. Hey. Wax on, wax off. Wax on, wax on. Hey, wax on, wax off. Concentrate. Look at my eye. Not the hand. Thumb inside. Wax on, wax off. Wax on, wax off. On, axe off. Show me pentafence. Up, down. Up, down. Up, down. Other side. Look, I always look, I. Show me penthouse, side. Knucklist. Side. Show me wax on, wax off. Catch! 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 Show me interface. Catch! Face! Catch! Catch! Show me side of thing. Catch! 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 Show me center floor. Catch! Face! 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 Yes! Stop!
Very interesting. So what do we see here? We see a teacher breaking a complex task into multiple skills, having the student practice those skills separately, and then we saw how quickly, extremely quickly, that learner was able to assemble those skills into the composite task. This is interesting. We did something very, very similar when we taught a robotic arm, a Jayco robotic arm, it's a 7-jointed robotic arm, to grasp and stack blocks on top of each other. So when Google DeepMind did this, they used a more monolithic approach, and it succeeded. It took about 1 million iterations, a million practice decisions. But when we broke that task into 5 modular skills: reaching, extending the arm out from your body, moving your arm laterally from your shoulder, orienting, turning your wrist to get your hand in the right position to grasp the block, grasping, which is really about fingers, and then stacking, which is about your fingers holding onto the block, but also that lateral shoulder movement. The selector, that supervisor AI, learned how to complete the task in 22,000 iterations. So instead of 1 million, we're talking about 22,000 iterations. It's the exact same thing that's happening here with this karate student. When he practiced separately and the known skills that were given to him by his teacher, it wasn't like he was, the teacher's telling him exactly, the coordinates to move. He's giving him a skill to practice. And when we do that with AI, the AI is able to combine skills into complex tasks very, very quickly and effectively. So you might say, well, Kent, that's all nice. You're showing me, movie clips, but where's the research? Don't worry, we got you covered on that too. DeepMind has a great paper they released in 2019 called Ray Interference, a source of plateaus in deep reinforcement learning. And here's one of the things that they say. Improvement in one component forces learning to stall or regress for the other components of the objective. Only after such a dominant component is learned and its gradient vanishes will the system start learning about the next component. What it's saying is, and this is true for humans too, if your task has multiple skills that go along with it, the karate blocking system obviously has multiple skills involved with it. Grasping and stacking obviously has multiple skills involved with it. Reaching, moving, orienting, grasping, and stacking. Then it's difficult for neural networks to learn multiple skills simultaneously. It's difficult for humans to learn multiple skills simultaneously. And what the paper is saying is that the neural network will get confused, and because it doesn't know where one skill starts and one skill ends. You can see that here on the left-hand side of this picture. I circled it in red. What these blue lines represent is they represent skills. Kind of these vectors are representative of the skills that need to be learned. And on the left-hand side, it's confusing one skill with the other. That's my colloquial explanation or terminology for what's happening there. But it's true. It's getting confused about when one skill starts and the other skill ends. Now, when you use reinforcement learning with a table instead of with the neural network, you see that it doesn't have the confusion. The skills are the vectors of the skills are separated. But we stopped using tables a long time ago because the neural network allows you to learn much, much, much more complex tasks. It's a universal function approximator. So we see that neural networks, just like humans, get confused when you don't tell them what skills are involved with the task and you ask them to complete the task. The performance plateaus observed in Atari when deep reinforcement learning was playing Atari games might be due to learning multiple interfering skills, such as picking up pellets, avoiding ghosts, and eating ghosts in Miss Pac-Man. So one of the first feats of deep reinforcement learning in 2013, this was done by Google DeepMind. They basically invented deep reinforcement learning, or pioneered deep reinforcement learning. Reinforcement learning has been around for quite some time. One of the first things they did was have it learn a bunch of Atari games, but there was a couple games that it didn't do so well at. Pac-Man was one, Montezuma's Revenge was another. These are games that require multiple different skills and strategies to be used at multiple different times. And here's the thing. The problems that you're working on, we're talking a lot about games because we're getting into the research and the benchmarks of research, and I'm providing you with some real examples, but also some research examples. But the problems that you work on, and a lot of those problems in those 100 brains that I designed require multiple skills and strategies. If you talk to the person who makes that decision for a living and they can fill a whiteboard with all the skills and strategies they use, then this is going to happen for your task too. For example, consider three components, A, B, and C, where A learns first and suppresses B as before. Now during this stage, C might behave in different ways. It's basically saying it's learning each skill incompletely. This new stage of learning is really slow, resulting in a long plateau of overall performance. And what's even worse is that the more separate skills that are required. So if the karate blocking system has, 2 skills or 5 skills or 9 skills, or the robot, task requires 10 skills, the more the skills, the exponentially longer it will take to learn those skills. So if it's 2, it's 10 to the 2. It's 3, it's 10 to the 3. If it's 4, it's 10 to the 4. And it gets to the point where you get something like walking, learning, unassisted learning at evolutionary timescales. So what are we going to do about this? Well, I propose a framework for our architecting modular brains, where the first thing that you do is you sit down with someone who knows how to do this. Now, it's different if there's no expertise. Critics might say, well, there's some skills where there's some tasks where there's no expertise. Fine. So, if nuclear fusion gets invented tomorrow, who knows how to control a nuclear fusion reactor? Nobody. Great. Use an evolutionary algorithm to explore the space, or use Monte Carlo tree search if it's it's a discrete problem, or use simulated annealing or unassisted DRL to search the space. Great. But most of the problems that are modeled in AnyLogic are problems where people have existing expertise. Scheduling in warehouses, routing, all these kinds of things. So the first thing is you identify the skills that you want to teach. You identify the functional concerns and heuristic strategies. Then you do that, frankly, by sitting down with someone who does this for a living, who really knows. And this can be one of the challenges, because we're bridging here AI research, kind of hot off the AI research press with, and we're applying it in areas that are pretty far from AI research, logistics and et cetera. So it takes a lot of curiosity. It takes a lot of listening to sit down with an expert, speak to them in plain language that does not condescend them or condescend to them, and want to know about their expertise so that I can design an AI that will learn the specific skills. Then you figure out, once you figure out what are the skills that you want to teach the AI, then you figure out how the concepts work together. And I'll show you some examples of that in a minute. How do the skills work together? Do they need to work together in a sequence? Are they in a hierarchy? Do they get used at the same time in parallel? All these kinds of things. And then you select the decision-making technology for each brain module. This isn't actually a framework or an approach that's about deep reinforcement learning or about any other particular technology, because some technologies are better at making certain kinds of decisions than others. So like I just said, if there's a large space that you have to search for solutions, there's lots of optimization algorithms that are really, really, really good at that. evolutionary algorithms, simulated annealing, all these kinds of things. If you need a very predictable decision that's going to happen the same way every time, that's going to happen quickly and reliably, well, control theory is great at that. Expert systems are good at that. But if you need a decision that requires complex perception, the ability to respond to prediction, the ability to find complex patterns, the ability to look ahead and plan ahead, and come up with creative solutions as you're doing decision making, then deep reinforcement learning is a great technology. But by all means, identify the skills you want to teach, then figure out how the skills work together, and then put deep reinforcement learning where it should be used, and put other things where it should be used. And that leads us to 3 different kinds of skills or concepts that we'll design into brains. 3 different types of skills that we're going to teach to these AI brains. The first, and we use workflow diagramming. We're not going to reinvent the wheel here when we visualize these things. Workflow diagrams are already really good at showing decisions that need to be made, selections that need to be made, and things that need to be processed. So great, let's use workflow diagramming symbols. So in workflow diagramming, a hexagon is a preprocessor. But there's perception skills. Perception concepts process sensory information to perceive, predict, classify, detect, or filter. This isn't the sensor. Like your eye isn't just a sensor. The rods and cones in your eye are executing a perception skill that's helping your brain identify or detect, and perceive what's going on. So perception is processing the sensory information in order to predict and classify, detect, or filter. Then there's action skills. These are the money makers here. They're making the decisions based on the perception and feedback in the brain. Now remember, this could be deep reinforcement learning. This could be an expert system that's taking this action. This could be an optimization routine that's taking this action. This isn't a tribal warfare over different types of algorithms that that we like. This is a framework for how to develop autonomous AI that far outperforms any of these techniques alone, and in a lot of cases humans also. I'm giving you the tools to do that. And then selector concepts, they supervise and they assign decision-making control to brain modules for performing skills. So selectors decide who's in charge of making the action. So let me give you some examples. Sometimes you organize skills. So the building blocks of brains are skills. They're not algorithms. They're not any of that. The building blocks of brains are skills. So sometimes the skills are arranged in sequences. And that's this is the robotic arm work that we were doing where, you're reaching, that's one skill. You're moving, you're orienting your hand around the block. Hands are called end effectors for robots. End effectors are robot hands. You're grasping and then you're stacking. Okay, so there's a supervisor selector module that decides, when to activate the reach skill, the move skill, the orient, the grasp, and the stack skill. And it actually learns to do that. So it learns by practicing. It practices, imagine what would happen if you tried to grasp the block or you tried to stack the block before you grasped it, which it would do that. It would practice and it would say, well, let's try the stacking motion, but you don't have the block in your hand. Well, you didn't succeed, surely. But what happens if you try to grasp before you even moved over to the block? Well, that's not going to work either. And that's okay. This AI is going to practice and it's going to figure out, oh, I get it. I need to orient before I grasp. There's a sequence here. I have to orient and get my hand in the right position so that I can grasp, or else the grasp won't be successful. And I've surely got to grasp before I try to stack, because it doesn't know any of those things that we think are intuitive. Of course, this AI, which sometimes we think of as a human, doesn't have human reasoning, and doesn't have a library of kind of things that it already knows. So it tries anything. So this is the brain design that we used for that research, and it shows you how you can sequence functional skills. And one other thing I'll say is, as you can see, this entire AI is not deep reinforcement learning, nor does it need to be. Reaching and moving in robotics is very well understood and well calculated with a technique called inverse kinematics. Great. So how did we get this brain design? We assigned the skills. We learned the skills that need to be done. We orchestrated the skills. They need to be done in a sequence. I want the brain to learn the sequence through a selector. And then we decide what should be what. Orienting your hand around a block when the block might be different sizes and shapes, and grasping a block that might be different weights and different center of gravity. That needs to be learned. That's going to take practice. That's a very fuzzy skill. But reaching and moving is well known. Great. So use inverse kinematics for the first two modules and learn the other four. Now, sometimes you arrange skills in hierarchies for strategies. So this is what happens in chess and in many different games, where at times, depending on the situation, depending on the board position in chess, or depending on how the defense lines up in football, you're going to use a different strategy, and different strategies will become more effective and will become more appealing at different times, even though they're always relevant. So unlike sequences, it's not relevant to try to grasp the block before you, to try to stack the block before you have it in your hand. That's not a valid way to stack blocks. But strategies, they're all relevant at different, they're all relevant, but at different times, different strategies become more appealing. So let me give you an example. So I designed some brains for crushing rocks in this these mining crushers. So pretty much every mining company uses a rock crusher at the very beginning. So when the big rocks come, off the mountainside or wherever they're coming from, they go into this cone. It's like multiple stories tall of a steel cone, and it goes in, and there's a gyrator in there that's smashing the rocks up against the side and getting them to be smaller. You succeed when the rocks come out a certain size and can go on to the next stage. And so they go through this kind of shaking sieve, and if they make it through the shaking sieve, they've been crushed small enough. They told me there's pretty much everyone that I talked to across various companies told me there's two different ways to operate crushers. You can stuff them chock full. And if you do, it's like just so jammed in there that it has a lot of force to break the rocks. That is a strategy that's very efficient. It crushes almost everything the first time. But here's the trade-off. And with strategies, there's always trade-offs. So it's never about, just optimize this. And that's the thing when you're talking about, objective functions and optimization, there's often different strategies which would have completely different objective functions. That's how you get into these reward functions that have 2 and 3 and 10 terms. It's very efficient, but it's slower because it's jam-packed in there. It takes the rocks a while to get through there. Now, if you regulate the crusher, you don't stuff it chock full. Things go through a lot more quickly, but it can't crush the largest, hardest rocks. So one of these strategies, the choking strategy, is really good for large, hard rocks. So it'll crush them the first time every time. But it's not good for small, soft rocks because they're going to get crushed anyway, and it's just going to slow them down. The regulate is a good strategy for soft, small rocks because they can go through faster. That's a strategy that emphasizes throughput when the rocks are softer and smaller. But if the rocks are large and hard and you regulate the crusher, the rocks are going to have to keep going back in over and over and over and over to get crushed to the right size. These are skills arranged in a hierarchy and acting as strategies, where each concept is trained to execute a heuristic strategy, including the selector concept, which learns which conditions to leverage or use each strategy under. I'm looking at my watch because I'm going to try to make sure that we leave plenty of time for questions. So I actually want to, at this point, stop and take some questions. And we have some other places that we can go and many more things that we can talk about, but I want to open us up for some questions. What are some of the ways to countermeasure local optima? That is a great question. So let's talk about So first thing you should know about deep reinforcement learning is deep reinforcement learning does have the ability it maximizes for future reward. So it does have the ability to learn beyond local optima. But because the spaces tend to be so big, my primary weapon is teaching known skills. So let's go back to the walking. That crawling on the ground business, like dropping down to your knees and then reaching out your first leg to like claw forward, that's a local optima. It's not walking. It didn't require you to balance. So the way to get beyond that local optima is to teach specific skills. Because if I'm teaching that to walk, you have to lift your leg, plant your leg, and then switch legs, then the local optima of dropping down to your knees is nowhere involved. It's not even an option. One of the other local optimas, it kind of looks like the McDonald's Hamburglar, just kind of tiptoe because it's so afraid to try to learn how to balance. That's another local optima for walking, for attempting to walk. That doesn't meet the definition of walking. But I think you can see how me teaching those skills that are involved in walking force the agent to practice the relevant skills and then allow them to combine the skills to get to walking and take off the table infinite amounts of local optima that you could get into. Can you elaborate on naturalistic decision making? Yeah, that's good. That's good. So AlphaGo and AlphaZero, Alpha Chess, when you see it making decisions, the chess grandmasters and the Go masters called it an alien playing style. They said this plays like an alien. This is not natural. And here's my opinion as to why that's happening. It's using a Monte Carlo tree search. So actually, AlphaGo was a modular AI too. You know, we call it an algorithm. It was not an algorithm. Like deep reinforcement, it uses an algorithm, but it's actually a modular AI too, because it used supervised learning to better classify and identify board positions. It used deep reinforcement learning to, in a way, select strategy. It just, there's a lot of nuances there, but it used this thing called Monte Carlo tree search to actually select the moves. Now, this is how Monte Carlo tree search works. Some of you guys know this already, but just for everyone else's. Monte Carlo tree search is looking ahead. It's like reconnaissance. It's looking ahead to all possible moves. So in chess, there's on average 31 possible moves at any board position. So there's 31 possible moves. But then the tree branches out, because if I make this move, depending on what the opponent does, then there's X number of possible moves at X number and X number, and it becomes this gigantic branching tree. Like the tree for the number of options in chess is in a 40-move game is going to be more than the atoms in the universe. And in fact, checkers was solved. So an algorithm searched for 20 consecutive years of compute and looked at 500 billion, it was either 5 or 500 billion options, and looked at every possible option that could ever happen in checkers. It's solved. Now, for the rest of us, because of uncertainty, because of the number of options, we can't just go and look at every option. And so Monte Carlo tree search randomly jumps into the trees and looks at different parts of the tree. And then it tries to find in chess, they call this a line. It tries to find a line at the end of the tree. There's only I win and I lose. I win in checkmate or I lose in checkmate. So, with the Monte Carlo tree search, if it randomly, it can only search so many times. I think for AlphaZero was like 72,000 times on average per move. So it does 72,000 random searches, and if it happens to get on a branch that ends in a line where I win, it follows it. And it does anything to follow that line. It'll start sacrificing pieces. It does whatever is necessary to stay on that line. But next time, it might find another line, or it might not find a line that goes completely to the end. I believe that's what makes it a alien playing style, because it will just jump to something it randomly found. That's not how human chess players play. There's a lot of great psychological research, and this is to your question. Chess players, they look ahead, but when humans look ahead, we eliminate the moves that don't make sense. we eliminate the moves that don't make sense for the strategy I'm using, and we eliminate the moves that don't make sense for the strategy the opponent's using. So instead of there being a huge tree that you have to randomly search, it's a much smaller tree because we've filtered out so many things because of our bias, strategy as our bias. So I think that's one of the keys to more naturalistic playing. Why is future reward so important? Because otherwise I'm only going to do what benefits me in the short term. So it doesn't benefit a squirrel at all to store up in the moment, to store up nuts for the winter. And it doesn't benefit a bear at all in the moment to get fat. He only does that so that he can survive the winter. So if you only do things that benefit you in the short term, then you will not win in the long term in a lot of realistic systems. Out of 100 brains you've developed, what kind of problems are a good fit, you think, for DRL? That's a great question. So one of my favorite rules of thumb is if humans are around making decisions, it's because the automated system couldn't. And so that happens in two ways. Sometimes the automated system works and then fails under certain conditions and the humans rush in. So I worked on this use case where they're making aluminum. There was an expert system. The expert system does very well, but under certain circumstances, it was really the fuzzy boundaries between one strategy and the other. The expert system didn't do well. The alarms went off. The humans rushed in and made a decision. So I see it over and over. If in your supply chain, the optimizer doesn't do well, and then the humans rush in to make a decision, that's the only reason the humans are rushing it to make in because more human-like decision-making is required at that time. It's usually because of fuzziness, nonlinear relationships and correlations between variables, or the need for strategy, or this kind of forward thinking and planning that the algorithm's not doing. Some decisions, the automated system can't do it at all. And so humans are the only ones that can do it. Those to me are shoo-ins. But I always ask, what are those humans doing over there? And they usually tell me it's because this automated system doesn't behave well. So I'll give you another example. Dijkstra's algorithm, right? So when you're doing route planning, and you're, for example, a rental car company came to us. They said, hey, in Detroit or Phoenix or whatever city it is, we have 15 locations. And every day, about 100 cars need to be moved around to different locations. And so there's a human planner writing down a schedule for each of the 10 drivers to go and deliver things. And one of the first things that folks said to me was, internally, was, why are those people doing that? Dijkstra's algorithm can plan a route. Well, Dijkstra's algorithm and other algorithms use nearest, they plan for you to be, your next stop to be as close as possible to the current stop. But think about this. The thing that makes delivery the hardest is traffic. Traffic can render the nearest stop as the worst possible thing you could ever do, depending on the traffic conditions. And traffic is something that has patterns to it. It's not random. It has patterns to it. Commute traffic is the worst on Thursday and Friday nights, and it's the lightest on Tuesday and Wednesday nights in the city of San Francisco. So an AI can potentially learn those patterns the same way a human can. There you go. More human-like decision-making, better decisions than maybe Dijkstra's algorithm. Can I conveniently apply to simulate an athlete's performance? The human behavior stuff is difficult. I had a company come to me once and said, we want an AI to provide incentives to our workers. Now, here's the problem with incentives to our workers. Then you have to model how humans are going to behave. So if you have a lot of data and you have, behavioral psychologists that say, here's the 5 behavioral patterns and here's the statistical likelihood of each of these behavior patterns, and here's the statistical distributions and all that, then you could do that. But you got to have feedback on what the humans are actually going to do. And that gets really difficult. That can get really, really difficult. Another question. Is an RL agent able to keep up with a rapidly changing real world environment? Yes, it depends on how rapidly is rapidly. So a well-trained DRL agent that has been shown all relevant scenarios. So it's not possible to show it all possible situations. You don't care about all possible situations. You care about all relevant scenarios. So for that crusher, the relevant scenarios are large hard rocks and soft small rocks. So if you train that thing only on large hard rocks, it's not going to do well. But if you train it on large hard rocks and small soft rocks so that it can know the difference and know which strategy to apply, it can absolutely respond really, really well. Now, there are limits. For example, the Bonsai platform is, living in the realm of, 30 hertz. So if you're doing low level control at like, 100 hertz and things like that, that can be a little challenging. I think that is all the questions. Are there any more questions? Please feel free to drop them in. These are really, really good questions so far. Yes, is RL different than machine teaching? So RL is the learning algorithm. Machine teaching is designing the modular AI such that you're biasing the learning based on what you already know. Teaching fundamentally is bias. So I know bias is like a dirty word, right, in AI, but teaching is bias. So when a basketball coach says, when you're close to the basket, shoot a jump shot, that's a strong bias. It's also a bias backed by a lot of physical realities and a lot of data. So he's basically saying, you are significantly handicapping yourself if you decide to go it on your own and find some other way to get the ball in the basket besides a layup when you're right next to the basket. That's what teachers do. And the more confident we are of the skills, the more experience we have exploring the space, the decision-making landscape, the more confident we can be in our biases. RL searches naively without any bias. It's not naive as in it's like not effective in searching. It's just it doesn't have any of the reasoning or the biases that we have. So in Pac-Man, when an AI is going to play Pac-Man, it doesn't know what a life is. It doesn't know what a ghost is. It doesn't know what a fruit is. It doesn't know what a pellet is. It doesn't know what any of that is. So it's exploring at a much more basic level than we even think it does because of anthropomorphism. So teaching is just enforcing what we already know as landmarks in structure to keep from exploring all sorts of things that make no sense. So for example, if I'm a robotic arm, I'm just about to grasp the block. And if I allow you to move your elbow, so when you're about to grasp the block, the skill you need for grasping is what? Your fingers. You need to do this. So if a naive RL is going to allow you to jerk your elbow. And so you might grasp with your fingers, but you're obviously not going to ever grasp the block like this. There's an infinite amount of things that you can do when it's time to grasp besides this. So me telling you to only move your fingers when you're about to grasp the block is preventing you from exploring infinite numbers of things that could never possibly lead to success. That's what teaching does. Is there work on explainable AI so that humans know and to trust the predictions or actions of the AI? Lots of work on explainability from the algorithm and the ML perspective. I'm not an expert in that. But these networks of modular AI are more explainable because than the black box of a single DRL agent, because let's go back to that crusher. The selector that's making the assignments says, hey, this isn't just what you should do with the crusher. I'm letting you know I'm choking the crusher right now. So it's telling you what skill it's using, which is a little bit of the why. That can be very valuable explainability. So you can, for example, validate. So I've had people tell me there's certain skills that only expert operators get to use because it's dangerous if you do it at the wrong time. So if you have a modular structure with a supervisor that learns when to use the expert skill and when to not use the expert skill, you can treat it like an expert. But if it's a black box and it starts doing that, you have to assume that it's doing something unsafe because you didn't explicitly teach it that skill and validate that it knew when to use that skill. The modular AI allows you to do it. It allows you to do that. All right. If there's no more questions, it has been absolutely fantastic being with you. If there are more questions you come up with, feel free to contact me on my profile. Thanks, and have a great day.
Thanks, Kent. Amazing presentation. Thanks for breaking things down for us. Made things a lot easier for me to understand, and I'm certainly, it was great. I appreciate it. We have a lot of great comments coming in on the chat, and offline I see a lot of other comments of how simply you've made this easily understandable. Thank you very much for your presentation, and great having you here. And again, if anybody wants to ask Kent some additional questions, please feel free to reach out to him, as he said, either on his LinkedIn profile or certainly on his profile here on the platform. Under the presentations, you see the icon and simply ask the question there. Thanks.